Thank you for inviting me here. It's a great pleasure to be again in Budapest. Title is a little bit complicated, but I hope I will have time to explain the title at least. And I start with some notions of geometric pressure for rational functions. The first definition, I think most fundamental, is variational pressure. Or no, this I believe. But, remind you, we are on the Riemann sphere. Here, Julia Setis mentioned it. Julia Setis is a big chaotic repeller in the sphere. Periodic orbits are dense. This can be taken as a definition. Repelling periodic orbits. This is closer. Yeah, there are other definitions. And this is for phi. I wrote phi as minus p log f prime, but actual value of f prime, but it can be defined for any continuous potential. By the way, here this log f prime need not be continuous at critical points in Julia set. So not just example, and it needs some theorem that log f prime is always integrable, and even for every measure. And here I wrote an explanation why it is related to Hausdorff dimension. It somehow explains why to call it geometric pressure. And that's because you can write equilibrium, you can take a good measure, equilibrium measure, and use T, and you have by Shannon, Macmillan, Brayman, or just by construction, because I assume it is hyperbolic. Otherwise, there are complications. So measure approximately x minus m h is entropy, and diameter is explained due to Birkhoff-Ergodic theory. It's more or less exponential of minus n characteristic Lyapunov exponent, and then you have what is due to the fact that we take T0 so that pressure is zero, this variation, and then we take such a measure, and then we have what is difference here. That T0 is ratio as entropy divided by Lyapunov exponent. We have this formula, and if this formula measure the approximate diameter in power T0, I hope you all know it is then dimension of the measure. If it is equilibrium, then it is the dimension of the set. To measure Julia set, which might contain critical points, might be complicated one, anyhow, always approximated by hyperbolic subset, invariant hyperbolic subset. So this is so-called what I explained it to generalized bound formula, and the first zero is hyperbolic dimension. It's not always true that the first zero of the pressure, if it stabilizes into zero after some parameter, Hausdorff dimension might be somewhere on this line, the horizontal line of the graph. Zero is hyperbolic pressure, and is defining both notions, hyperbolic dimension and hyperbolic pressure. As I told you, I use it to approximate by hyperbolic subset. And here both notions to compare them are hyperbolic. So what I will discuss three pressure. The formula is the standard one, but here. I forgot to say, let me remind you that pressure is kind of in this variation of, in this definition, you take all backward trajectories. So it is like partition. So it is normalizing factor when you use it in equilibrium statistical physics. Instead of the point, you could just take cylinders. This is so-called partition function normalizing to distribute measure. Distribute measure according to derivative iteration, you need to normalize it. And this is sum over all backward branches or over all cylinders. And that explains why this definition is appropriate and coincides with this variation. And one can define periodic pressure just as periodic orbit. And the problem is the periodic pressure, geometric periodic, the same as the other notions of pressure. So the problem was open since a while, more than 20 years. Smirnov tried to do something to expose something about it, and they proved it for polynomials, but actually there are no indifferent periodic orbits. It means periodic orbit is derivative of the composition, the period derivative of having absolute value 1. And I think, I know it says true. I mean, I will attempt, I think I know how to prove that it is really so. I will verify hypothesis H, which is needed to next slide. The for quadratic polynomials. So at least for quadratic polynomials and for also unicritical polynomials, means d in the power d, at least 2, but maybe bigger than 2 plus c, it also works. Whether it works for all polynomials, I don't know. Work for future, but hopefully yes. So I formulated this question. So this question was formulated in my paper in Juan Rivera career with South Smirnov, and I repeated this question in my proceedings for IMS in 2018. So this is this hypothesis. Which means that I need to know that there are not many, exponentially many periodic orbits going in a bunch all together, which in distance exponentially small. At most x delta n. The orbit can be in such balls along the orbit of diameter x minus delta n. So I will try to sketch the proof, and it goes in this remark is important. I was involved for many years in topological Kohler-Ekman maps, which is generalization of Kohler-Ekman. But one of the definitions is that if you take a small ball, a disk, then units, there's pullbacks, components of grain, pullbacks have diameter shrinking uniformly to, or exponentially to 0. You can imagine that if we have many periodic orbits going together, but periodic, then it's not, this backward shrinking cannot be satisfied. So that's why topological Ekman roughly satisfies it. This is also in my paper, in my paper with Rivera and Smith. Anyhow, to prove this hypothesis H, I will do it in 3 steps. First is this packet of periodic orbits is very close to Kramer fixed point. Another, if it is very close to Kramer periodic, and then a general case when they are just going together periodically, but we don't assume anything about Kramer. What is Kramer? I forgot whether I told you already or not. Ah, it is here. So just if we have rational fixed point or periodic, we know what happens there. There cannot be periodic orbits nearby, but it is different if it is irrationally indifferent. Then we have rotation number for linear part because derivative is x I 2 pi I alpha, and everything depends on how fast this alpha is approximated by rational numbers, continued fraction development, and the definition. I will discuss it later. And the strategy of the proof, maybe not strategy, I told you strategy, but the main idea is to use Milnor. This is Milnor book. Milnor book, everything is explained, but there will be another Milnor reference, will be later, explaining what is really the mechanism of my proof. To explain what about this periodic orbit close to Kramer fixed point, there are rather old papers by Ricardo Perez Marco. It's a theory he did under guidance of Yokos in his PhD. And there are 2 theorems that if we have very fast growth of fast growth of Qn. These are ratios Pn over Qn in continuous fraction that approximate the number. These are called convergence. This first condition is called Bruno. The Bruno condition is not satisfied. Fast approximation, fast fluvial property. Then we don't have linearization. Otherwise, we would have Ziegel disk around such points, but we assume my point is I work in Julia set. I'm not interested in the case we have linearization. I am interested in the other case, which is called Kramer, satisfying this condition for, but on the other hand, the escape of Qn is not too fast. Then may happen since the many periodic orbits have grown converging in this Kramer point. If in fact we have equal infinity, even faster, then the paper of Ricardo is written that might not be any periodic orbit close to Kramer. So this is something between the appear. You know, there is a hedgehog around such Kramer fixed point. Rotation is irrational, but it is degenerated in this. So between there might be periodic orbit. So the question arises, how many? And if I can answer this. Here is the Milnor expository paper about combinatorics. Which I will apply. A simple lemma, but the paper is difficult because the paper. No, it's not here. Or maybe it should be explained later. But it's important what I wrote here that usually the doing it in polynomial case and especially in quadratic, everything becomes easier. It is not complex. It is dynamics on the circle, external rays going to points in the Julia that I will tell you in a moment what I mean by this. So this is dynamics of mapping z square on the unit circle. Which is easier. Here is some notation. In Julia circle like this. No, I think important is that the and that I consider these external rays, which are images of I use Riemann matrix here. Oh, it is here. I see map conjugate z square to z square plus c. In case Julia set is connected, then we have Riemann matrix from basin to infinity to basin to infinity. Images of radii in the disk are called external rays. And arguments of these radii are external arguments or external angles. Here is a picture from Milnor's article. We have external rays. I will try to explain it very well, but there is these are two partitions of vectors. We have orbit of period 2 here. First, we have here perturbation basilica, and then after basilica, we have rabbit in bifurcation. So it is rabbit inside basilica. What is the smallest? We have two sets of sectors between rays going to the same point. The smallest one is containing critical value. 0 is critical point, that is the biggest component, and then dynamics of these angles is just multiplying by 2. At some point, we grow to more than half of the circle. And then we cover, then we somehow, then critical point works, and we obtain not injective method. I'm trying to follow this exercise, you know. And here is this portrait. It's portrait. Again, you have two orbits at period 2. And here is critical point. Here is critical value. You can check that you have multiplication by 2 of the angle. And the following lemma, which I use, is that this portrait J are set of external arguments corresponding to one point, J point in the period orbit. So we have P such J's. And the following properties are satisfied. This is an easy lemma. That each set is non-empty and finite. This is not the case. The periodic point is attained by external array, and there are a most finite number of such arrays. The second follows from famous very easy dilemma. If you have compact subset of the circle, and the restriction of this square is monotone, then the set is finite. So we have properties here. Especially the second is non-trivial, that we have bijective, so reserving cyclic order, this mapping from one rate from one point to the next in the orbit. And another is that we have pairwise unlinked sets of rays from one point. You can see these rays from one point and these rays here, they don't, the endpoints must be separated because of separation by rays. The rays cannot intersect. Yeah, formal definition. So my proof, I will try to somehow create something similar to such formal orbit portrait and checking the assumptions. Because now comes the theorem that we have transitivity, that we have at more, well, rays create also some orbits. These are invariant sets. We have periodic orbit point, but every point has some rays landing at it, and we have also periodic, ray periodic situation. And the question is how many orbits? So the theorem says at most two, or sometimes even one. And so we have such a transitivity, which means that if we have many periodic orbits creating this formal portrait, then it is a contradiction, because many more than two lead you to a contradiction on the impossible on the level of rays, so even more on the level of points in the orbit. By here, there are two cases, primitive and satellite. And primitive is if some new in parameters Mandelbrot set is born from nothing, like period 3, famous, where everything grows from fixed point, and satellite is just bifurcation. And here in this picture, we have satellite situation, because these rays go not to something fixed, but to periodic thing. So R is just number of orbits. So over one point is number of orbits over one point of the periodic trajectory. If R is equal V, then it means all points are visited over one point. It is one trajectory. If it equals 2, then it means there are 2 orbits in rates. After. Yeah, there is nothing special. Definition, but what is important is how to know in that there is a minor case that the cyclic order is preserved because we have points, say we have fixed points. We have rays starting from one point when we take image. So locally, at the fixed point, Kramer, yeah, or not Kramer or Feliks, at the fixed point we have homeomorphism. So homeomorphism preserves order of rays that start from or that land at this point. But then this goes to infinity. We are interested in external arguments of infinity, but Jordan's theorem does not allow to change order because rays cannot intersect each other. So the main problem in what I working on is that I discuss now points not being just one point and fixed point, but points of this of length n, of period n, starting close to Kramer. And the whole orbit is close to Kramer. So it is like fixed point. But there are some gaps. So I need to be careful to know that rays do not come back and go through a window between two other rays. First one needs to define local definition. No, maybe it's useful. Maybe what is how to see the cyclic order, the right one close to Kramer point, and we take a small circle, and for each, but encircling all the points in my packet points, the other points, and I consider the last leaf of the disk as my rays using order on the circle do not come back, then again Jordan's theorem will say that it has the same order of infinity. So this is it's written what I described. You know, I replace R by R prime. And here is the crucial point. It says that, let me make a picture. It says that we have this thick line, this part of the circle at infinity, the matrix F has degree 2 on this because we have critical point 0 inside. But the image of this thick line without this circle, it is growth of argument is less than 2 pi. Follows from the picture. So on this boundary arc, growth of argument is bigger than 2 pi. So on the complementary arc, which I call regular, all other arcs together, it is at the image less than 2 pi. So the arc is less than pi. So the conclusion is that the mapping Z square on union of all other arcs, not those that have the factor critical point union, the mapping Z square is injected from this. So you have monotonicity. And we don't, I didn't tell you about this sector, this critical sector, but it doesn't matter because rays bound other sectors. And I was fighting with this for a long time, by trying to prove by hand that the rays cannot go through some windows between other rays, etc. But joining all the rays together and considering a domain solves it. This is almost a zero time. Oh no. No, but I need to human. Okay. So this would be done. We have order preserving. Then for Kramer periodic, or order preserving between consecutive points of the Kremer orbit proof is the same. Troubles are this unlinkage, because again, a race from one point starting close to one point in the orbit can go through other, and one should again modify definition of these rays, making them shorter and shorter, not too short, because we are interested in the angles at infinity, not the angles somewhere. So we can shorten the ray. And now the last sentence about this hypothesis H. Two things we can easily do is control of distortion and be sure we are far from critical points, because we are working with very small disks. If even we are close with the orbits to critical points, we can divide neighborhood of the critical point into annuli, and there cannot be too many annuli too close to critical point the orbit passes, because time of return must be of order at least log of the distance, because we have, even if we have critical point, then we have expansion, but if expansion is finite, not still this contraction, so otherwise we would have attractive periodic orbit, which is not so. And here is the final observation that what happens. I want to refer to Kremer, or not to Kremer, but to Kremer-like. So I start with small disk, which contains all these n epsilon closed points, and I take bigger, slightly, not slightly, but bigger disk, but multiplied. No, so small disk, if we have close return after some time, K1, then I take image, etc., etc., etc. And it must flow. The picture is not good because the last one should contain extra gain. I should mention that this distortion is very small, so in fact we have similarities between all these chains of disks. We have smaller, bigger, 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 and either, so we consider bigger disks, then times of return will be shorter and shorter. And either at some point there is no shorter return, which means that I have package of points, then par image of it, etc. It looks like periodic Kremer. Or I always have returns under shorter time, which are not much further than the previous return. And it repeats and repeats to the end. Then everything is small bit. I have situation like Kremer fixed point. And the time to exhaust all this is logarithmic, because each time I divide by 2 and after computation, I obtain diameter of the final disk, which goes periodical, like periodic Kremer or fixed point. Diameter is exponentially smaller, and which again means that I can use Kremer like observation, methods. Thank you.